Welcome back, I'm that chemist, and in today's important papers, we're going to be discussing some underrated reducing agents that you occasionally see used in organic synthesis. To provide an overview, the four reagents that we're going to be discussing are aluminum isopropoxide, Raney Nickel, red al, also known as Vitride, as well as the combination of trifluoroacetic acid with triethylsilane. Aluminum isopropoxide is a reagent that is readily accessible from aluminum and isopropanol. It can be used for a wide variety of purposes, such as an MPV reduction, but you can also use it for oxidations, such as in the Oppenhauer oxidation. Now, this can be viewed as a catalyst, since when it's used in an MPV reduction, isopropanol is the true reductant. This is just the catalyst. However, if you start cooking certain compounds with aluminum isopropoxide, it will also directly function as a reducing agent. Now, the true structure of aluminum isopropoxide isn't a trimer where you have three alkoxy groups connected to an aluminum, but rather, they form groups where they complex to one another, as polyalkoxy aluminates tend to be more stable due to the tetrahedral nature of the aluminum. Now, when you do an MPV reduction, as I was discussing earlier, you have something such as a ketone or an aldehyde, and this can be reduced via isopropanol through the use of a catalytic amount of aluminum isopropoxide. This then generates acetone as the byproduct, which can be boiled off. Practically speaking, the way that this is done is you initially mix the aluminum isopropoxide with isopropanol and your carbonyl compound. You then run the reaction to a reflux, and eventually you distill off your solvent. You add in some fresh isopropanol, and you repeat this until all of your carbonyl compound has disappeared via TLC. Now, you may need to use a different alcohol than isopropanol, or if you're doing an oxidation, you may use a different carbonyl compound than acetone. A common one to use for oxidations is cyclohexanone, and then in that case, you'd just be generating cyclohexanol as your byproduct. In reality, you'd be screening a variety of conditions to just see what works best if you're trying to optimize yield. But if you're just trying to get a few milligrams for testing, or you're just trying to push material, you'll probably just follow an established protocol and see what works. The synthesis of aluminum isopropoxide is typically done via the use of aluminum metal and isopropanol, with mercury chloride as a way to increase the surface area of the aluminum. But I want to give credit to Doyle, who repeated a procedure that he saw in the Explosions and Fire Discord, where gallium metal could be used instead of mercury 2 chloride. In addition, I've repeated this protocol, except I didn't use any iodine. The iodine's just included to help get the reaction started in case some of the aluminum's having a hard time reacting with the gallium, but it's not necessary. Additionally, this is a super duper exothermic reaction, and once that reflux gets it going, it's so exothermic that it will self-reflux, and you need to have extremely sufficient cooling in order to remove all the heat. In addition, because the aluminum is reacting with isopropanol, the OH group ends up liberating half an equivalent of hydrogen for every molecule of isopropanol. So this will also generate hydrogen gas as the reaction proceeds, which means that it must be done in a well-ventilated area. Once the reaction's complete, you're able to distill off any residual isopropanol that's present in the reaction mixture, and then subsequently, the remaining aluminum isopropoxide is able to be distilled in vacuum under reduced pressure. If you don't do this under reduced pressure, it will just lead to decomposition, but the aluminum isopropoxide is able to be distilled off even with a relatively weak vacuum pump. Now, it'll initially come over as a clear oil, which, if you're doing a vacuum distillation, this will probably be going into a flask. However, you should transfer it to a wide neck plastic container subsequently, otherwise it will solidify and you're going to have a really hard time getting it out without melting it. Now, earlier I was mentioning that aluminum isopropoxide can also be used as a reductant itself. The way that aluminum isopropoxide works is shown here with benzophenone. Initially, the aluminum isopropoxide forms a tetrahedral complex with the carbonyl of the benzophenone. Next, one of the hydrides from the isopropyl groups are able to migrate over to the benzylic position, along with the liberation of acetone, forming complex 5 as shown here. If this is worked up with acid, you're liberated with diphenylmethanol, but alternatively, if you heat this to 250 degrees Celsius, you'll instead have another hydride transfer occur, and you'll get diphenylmethane. This has been applied to a wide range of different aryl ketones, and as such, you're able to form these polycyclic aromatic hydrocarbon type compounds, although this high temperature of 250 degrees Celsius is still required. So if you're looking for a less toxic reducing agent, as opposed to something like a Wolff-Kishner reduction, which would use hydrazine, or a zinc-mediated benzylic reduction, you could instead use aluminum isopropoxide and just heat it till it breaks. Are you worried about side products? You can always just test this on a small amount and then see how it works. If you don't want to use aluminum isopropoxide or it's a bit too sluggish, you can treat it with trifluoroacetic acid, which forms this aluminum complex, which is a little bit more reactive. Here's an example where this aldehyde was reduced to the corresponding benzylic alcohol in dichloromethane at room temperature. This is similar to how sodium borohydride can be activated with acetic acid to generate triacetoxyborohydride or any of the intermediate acetoxyborohydrides. As mentioned earlier, the counterpart to an MPV reduction is an Oppenhauer oxidation. In this case, you can see both of these secondary alcohols are oxidized to ketones, and we also have the formation of a cyclopropyl group via activation of this mesylate with aluminum isopropoxide. This then allows the electron density on this alkene to attack at that primary position, forming the cyclopropane, as well as a tertiary carbocation. The tertiary carbocation makes the adjacent methylene group very acidic, which results in deprotonation and formation of the alkene, giving this alpha-beta unsaturated ketone, 31. The next reagent we're going to discuss is red al, also known as Vitride. Some benefits of this reagent are that it's stable in air, it's soluble in solvents such as toluene, and you can actually buy this as a 65% solution in toluene. And to simplify it, it's basically a better version of LAH. Now, red al can be prepared through a wide variety of different means, but the most simple conditions are to treat aluminum metal with sodium metal in the presence of monoglyme and in a pressure vessel with 100 atmospheres of hydrogen gas. The solution's heated at 100 degrees Celsius and then 190 degrees Celsius for 3 hours in benzene or a related solvent. You can also prepare the aluminum alkoxides first and then mix this with sodium and such, but this is the most practical method that I could find overall. But it's not as practical as just buying it from a supplier, but if you need a whole lot of it, you probably want to prepare this yourself. If you have access to pressure vessels, of course. Some of the applications are in the reduction of carbonyl compounds, which is similar to how LAH would. And in this case, we even have a peroxyketal, which isn't reduced by the red al, but instead only this ester is reduced to the corresponding alcohol. In addition, this example shows a stereoselective reduction of this ketone to the corresponding alcohol. We can also reduce amides to the corresponding amines, and finally reduce this ketone to the corresponding alcohol without touching this dithiane. If you wanted to reduce that dithiane, you could probably use Raney Nickel, but typically as chemists, we prefer to select one part of the molecule to reduce over the other. And certain aluminum complexes like LAH may struggle, and you may see a bit of degradation of that dithiane. If you want to compare the reactivity of some different hydride-based reducing agents, this is a table from Almonds which compares the different reactivity. In some cases, LAH is also able to reduce stuff like alkenes, especially if they're activated, such as Michael acceptors, including Henry adducts, and that doesn't usually happen when you use red al. Now let's talk about Raney Nickel. Activated Raney Nickel is able to accomplish reductive desulfurization, where any sulfurs that you have in the molecule can more or less just be replaced with a hydrogen. Raney Nickel is an alloy made from dissolving nickel in molten aluminum and treating that resulting alloy with aqueous sodium hydroxide. Depending on the version that you're trying to prepare, there's a few different types of Raney Nickel which can be prepared by treating the alloy with different amounts of sodium hydroxide. However, it's important to note that Raney Nickel should usually be stored in water or an alcohol-containing solvent, and if you're trying to get rid of any of that alcohol, for instance, if you wanted to make an alcohol or water-free version of Raney Nickel, you can just wash this a few times with THF. However, the THF will still have some Raney Nickel suspended in it, and it must be quenched properly before disposing. Depending on where you work, there will be different protocols for how this should be quenched, so make sure that you're following an established safe operating procedure before doing so. It's important to note that Raney Nickel is essentially finely divided nickel metal, which is pyrophoric in air, and can spontaneously combust, especially if you have various volatile solvents near it. If you're looking to do a reduction with Raney Nickel, such as the hydrogenation of an alkene or an alkyne, hydrogen gas should be used, usually in the form of a balloon, or if you're doing a larger scale reaction, this will typically be plumbed into the reactor. So to show some examples, here's some vinyl sulfides where the activated Raney Nickel is just able to desulfurize that and instead put a hydrogen there. However, in this case, we have different reactivity in THF than we do in methanol. In methanol, we have a hydrogenation of the alkene as well. However, in THF, we only reduce the sulfide and we don't touch that alkene. It remains intact. In this next case, we have this cyclooctatetrene which is prepared via treatment with Raney Nickel in acetone. And in this last example, we have a thioimidazole, which is an isothiourea derivative, which is able to undergo desulfurization and just put a hydrogen in that place, forming a regular imidazole. Imidazoles can be challenging to synthesize in this selective manner, so this is a desirable way to do so. If you haven't worked with Raney Nickel before, they're really convenient reactions because it's basically just dump mix in an alcoholic solvent, filter out the Raney Nickel, concentrate on the rotovap, after filtering and making sure that you don't have any of your pyrophoric finely divided Raney Nickel still in there, and then you do an NMR to see how it works. It tends to be very good, and it just goes at room temperature usually, so it's quite a good reagent to use. Here's a few more examples where thiocarbonyls could be reduced. In this case, we have a nucleoside derivative where the thioamide is sufficiently converted to the corresponding imine, which is just an aminopyrimidine. This thioketone was also reduced to the corresponding benzylic methylene, and we also have this cholesterol derivative, which was sufficiently converted into the dihydro analog without reducing that alkene. Now, one of the neat things that you can do with Raney Nickel is if you also have hydrogen present, you can reduce the double bonds as well as the thiophene. So here this thiophene is just converted into an entire alkane. So this is like a masked alkane, and maybe for some reason it's easier for you to add a thiophene in your chemistry than it would be for you to add a pentyl group. In this case, we're able to form this cyclic compound from this dibromothiophene. Bromides are also typically reduced via Raney Nickel, but it's worth screening just to make sure.
So this is how the authors were able to make this compound, but I wonder if today's sponsor Reaccess has any alternative ideas about how we can synthesize this molecule. Today we'll be examining the retrosynthesis planning tool of Reaccess. We can paste in our structure as a smile string directly from ChemDraw. We can remove any published routes so that we can see any of the proposed routes that the Reaccess retrosynthesis planning tool can show us. You can change the result of a prediction by playing with the diversity and selected building block categories. The Reaccess retrosynthesis tool utilizes 3 neural networks trained on Reaccess data to generate synthesis plans. It breaks down product molecules into starting materials using extracted reaction rules, matching them against a library of building blocks. The algorithm iteratively resolves branches into available building blocks, displaying predicted reaction steps along with literature examples, based on similarity scores to estimate feasibility. When we look at the route that the Reaccess retrosynthesis planning tool proposes, we can see that there's a lot of steps to it. So while this might not be the route that we would actually take when synthesizing this type of molecule, it still shows us some different ways that this sort of motif could be created. I'm a bit skeptical that the presence of a phenol would be tolerated for this Friedel-Crafts, but if you think that this could be done, you can let me know down in the comments. Personally, I think the route that utilizes a thiophene and Raney Nickel is quite an elegant solution that actually showcases the value of this methodology. In any case, the retrosynthesis planning tool for Reaccess is able to help you come up with new ideas for your research. I'd like to thank Reaccess for their support of this channel.
In addition to sulfur 2 compounds, it's also possible to reduce sulfoxides and sulfones, and sulfinyl and sulfonyl compounds broadly speaking. So this doesn't just apply to thioethers or thiocarbonyls, it also works for a wide range of sulfur-containing compounds. As I mentioned earlier, Raney Nickel can be used to reduce various alkenes in the presence of hydrogen gas. Here, this highly electron-deficient alkene was able to be reduced without reducing the imine, the ketone, or the ester, affording this tetracarbonyl 59. This methylpyridine was also able to be reduced in the presence of Raney Nickel, affording the corresponding piperidine. You're also able to reduce N oxides as well as nitro groups. But for most nitro group reductions, you usually have to screen a wide range of conditions and find one that is not too messy. Last but not least, we have the use of trifluoroacetic acid and triethylsilane. This is a popular strategy for deprotecting molecules, especially in contract research organizations, for reductions and reductive deprotections. Usually these reactions can be done in chloroform or dichloromethane at room temperature, but you do sometimes see other solvents used as well. One of the applications is in reductive methylation, so here this amide is able to be sufficiently reduced to N-methylpyrrolidine, and oxonium type of species, which can be generated from the trifluoroacetic acid, can also be sufficiently reduced via the triethylsilane. So the trifluoroacetic acid helps generate carbocations, and then the triethylsilane comes along and acts as a nucleophilic hydride source. If you're wondering how triethylsilane is made, we can start with tetraethyl orthosilicate and treat that with 3 equivalents of ethyl magnesium bromide, affording this intermediate ethoxytriethylsilane. This is treated with acid to form the dimer via an oxygen bridge, and then subsequently converted into the chloride via treatment with ammonium chloride and sulfuric acid. To convert triethylsilyl chloride to triethylsilane, we just have to have a hydride source, such as this trimethoxyborohydride, but you can also use LAH, sodium borohydride, etc., if that's more preferable to you. So this is how triethylsilane is made, and you can prepare a wide range of different silanes through similar methodology using alternative Grignards. Or you can just buy it, which is easier. As I mentioned before, we have trifluoroacetic acid forming carbocations. So in this case, we have an adamantane derivative, which would form a tertiary carbocation, which was able to be deuterated with triethylsilyl deuteride. You can also reduce olefins, especially like enamines or vinyl ethers, vinyl sulfides. As we protonate the alpha position, this can form an imine, and then the imine can be trapped via triethylsilane. In the case of this indole, we would again form an iminium, protonate the 3 position. This makes the 2 position highly electrophilic, and then triethylsilane is able to donate a hydride, giving us the cis-only dihydroindole derivative. It's also quite often used for deprotections. If you treat Bock groups with TFA, you'll generate that tert-butyl carbocation, and it has to go somewhere. So since it's a carbocation that's being generated, it again can be quenched with triethylsilane to afford isobutane, which would then boil off out of solution when you concentrate it. This can be used for other types of reductions. Here's a case where 2 Bock groups are removed. And in this case, we have a methylene group, which is essentially like formaldehyde had reacted with an amine. So this results in the formation of a methyl group without cleaving this benzyl group. And this trityl group is formed as a carbocation, which is then quenched by the silane to form triphenylmethane. This unmasks the NH2 group, and the carboxylic acid group is liberated from where it was once connected to that methylene group, which became the methyl group on this nitrogen. In summary, aluminum isopropoxide, Raney Nickel, red al, and the combination of TFA and triethylsilane are all interesting reducing agents that have good applications in synthetic chemistry. I think these are underrated, but maybe you disagree. If there's any other really cool reducing agents that you think more people should know about, make sure you drop a comment down below. Do you have bigger synthetic problems? Do you have some synthetic challenges which would benefit from the attention of a skilled synthetic chemist? Are you working with a CRO or a synthesis on demand company who's running into some roadblocks? Maybe you're trying to set up your own synthesis in-house, or you're trying to draft some protocols as standard operating procedures for your company moving forward. I'm currently accepting a few more consulting clients if this is applicable to you. My expertise is in method development, especially in organofluorine and organosulfur chemistry. Throughout the year of 2025, I'll be accepting a few more clients, and if you want to get in touch, my email's here. You can also reach me on LinkedIn. Thanks for watching, and I hope you have a great day.